the Lambda app developed by your friends is displaying information about a train that's departing the Detroit station at noon, and it's traveling on the track between Detroit and Ann Arbor. So we have something like this going on. So maybe this point is Detroit. We have Ann Arbor somewhere on the map. And we have a track extending from Detroit to Ann Arbor. And we have a train. So maybe this is a train. Obviously, this is not the best picture, but it's traveling along this track. And this app is giving us some information about the train. In fact, it gives you several values of lambda t, which we know is a differentiable function, and it gives the distance along the track in kilometers from the Detroit station to the train t minutes after noon. So we see that after 37 minutes after noon, we see that the train is 16 kilometers away from the station, and so on. And not only that, we are also given the derivative of lambda prime of t between 0 and 37 as shown. So here, to emphasize, this is the graph of the derivative of lambda t, and this is a table of lambda t. Okay, very interesting. Let's take a look at the questions. For parts A and B, you may estimate values from the graph as needed. Sounds good. Find the times t between 0 and 37. And between 0 and 37, we see that that's exactly the time interval that this graph is giving us information about. And you want to find the times when the train is traveling at its maximum velocity. Give your answer as values and or intervals of t. Well, here, I think it's good for us to be on the same page between velocity and, say, speed, because obviously this question is testing distinction between the two concepts. It looks like part B is really the same question, but it's really asking for maximum speed, not maximum velocity. And the main distinction, I suppose, so going back up, is that the velocity actually has some information about whether you're moving to the right or moving to the left. For example, if I'm moving to the right from Detroit to Ann Arbor here as 5, not meters, I guess it's really kilometers per minute in this problem. So if I'm moving, say, 5 kilometers per minute to the right, then the velocity would be, say, positive 5 kilometers per minute. And if I'm moving to the left at 5 kilometers per minute, maybe that's going to be indicated by saying it's a negative 5. The rate of change is negative 5 kilometers per minute. So a velocity is really going to give us information about which direction you're moving. If it's positive, you're moving to the right. If it's negative, you're moving to the left. Whereas the speed is really just the magnitude. It's just the absolute value of velocity. So in both of these cases, so either way, whether you're moving 5 kilometers per minute to the right or to the left, the speed is going to be 5 kilometers per minute for both of these. Anyway, from that information, let's see if we can actually find the maximum velocity and maximum speed. So remember that the lambda t was giving us the position of the train. So lambda prime of t, so when I differentiate this with respect to time, well, that's instantaneous rate of change of position with respect to time, and that's exactly giving us the information on velocity. So for example, looking at this graph, at time of 10, we see that the velocity of the train is plus 1.5 kilometers per minute. So we know the train is moving at the instantaneous rate of change of 1.5 kilometers per minute at time of 10 minutes after noon. Okay, so that's very cool. But where is it traveling at the maximum velocity? Well, this is literally the graph of velocity because it's the derivative of position. So we just have to find where in this graph is our function the largest, and it's clearly the largest values are being taken between say, it looks like between 10 and 13. So the answer to this question looks like between 10 and 13. Let's move on to the next part. You want to find all times t where the train is traveling at the maximum speed this time. So in this case, we care about where is the absolute value of the output largest in this graph of velocity. And it's not too hard to see that's happening at the time of 27. Because at 27, you're traveling at the velocity of negative 2 kilometers per minute, and that's the speed of 2 kilometers per minute. That's faster than 1.5. You're just moving to the left instead of to the right. I'm not quite sure why the train is moving to the left here, but I guess maybe it's taking some detour. Anyway, so we know the answer to part B seems like to happen at time of 27 minutes. And let's go on to part C. Find the average velocity of the train between 12 p.m. and 12:45 p.m. Well, how do you find average velocity? Well, if I know the position at 12 p.m. and if I know the position of the train at 12:45 p.m., and then it's now really just finding the average rate of change between those two values. So it'll be change in position divided by change in time. So let's see if we can get some information on where the train is at 12 p.m. and 12:45 p.m. Well, this table really gives us that information. We know at time of 45 minutes after noon, so this is 12:45 p.m. We know the position of the train is at 36, and this is 36 kilometers away from the Detroit station. And you might be confused on how do you know where the train is at 12 p.m. Well, at noon, the train was exactly at the Detroit station, so it'll be 0 kilometers away from the Detroit station. So the two position values we have, we know the position at time 0 is 0 kilometers away, and we know position at time 45 is 36 kilometers away. So we just want to find the change in output over change in input. That's 36 divided by 45, because you're doing 36 minus 0 divided by 45 minus 0 here. So going back down, we know that's going to be 36 over 45. And I guess if you want to, you can simplify this. This is like 4/5. And they want us to include a unit, which is kilometers, I believe, per minute. So here kilometers is position, and we're dividing by time, which was in minutes. Moving on, let's try to estimate the instantaneous velocity of the train at t equals to 41. So if we have 41 in this graph, then this problem would be very easy, because this graph is exactly giving you the instantaneous rate of change of the train, or instantaneous rate of change of the position of the train. But the graph is stopping at 37, so we really can't get much information about what's happening at t equals to 41. But at least we have a table of the position of the train. So we want to find how quickly the train is moving at time 41. So we can try to use this table of position to approximate the instantaneous rate of change at time 41 by finding average rate of change for some time interval pretty close to 41. So there are many ways of doing it, but we see that 39 and 41 are 2 apart. 41 and 43 are 2 apart, so it really doesn't matter what you choose. But you can consider the average rate of change between time 39 and time 41. So what we're doing here is we're considering the average rate of change of the position of the train from time of 39 to time of 41, and that's going to give you an approximation for how quickly the train is moving at 41. For example, something that you do not want to do is try to approximate it by average rate of change between 37 and 39. That's probably going to be a worse approximation than picking, say, 39 and 41. But here I don't think it matters between 39 and 41 and 41 and 43. They're both 2 apart. But anyway, how do you find the average rate of change in position? Well, there will be change in position from 16 to 24, which is 8, divided by change in time from 39 to 41, which is 2. So it'll be 8 divided by 2. So it'll be 8 divided by 2, which is 4. And again, for the position in the numerator, the unit was kilometers. And we're dividing by the time, which had units of minutes in this question. So make sure to include the units especially when you're asked to include them. Let's look at the final part. During which of the following time intervals is the train stopped for the entire time? So the position of the train is staying exactly the same the entire time. Another way of saying that is that the velocity of the train is 0 for the entire time. So let's take a look at, say, this graph. Where is the train stopped? Well, the train is stopped when the speed or velocity, it really doesn't matter if there is 0, if the velocity of the train is 0 for that time, and that's really happening exactly between time of 15 and 24. So going back down, we know between 15 and 24 the train has stopped. So this one is wrong, this one is wrong, this one is true. 41, 45, I think we have to be a little careful, because this graph only gives us information until time of 37. So if we want information on 41, 45, we probably want to look at the table. So what's actually happening at time 41 to 45? Well, we see that at 41 we are at 24, and at 45 you're at position of 36. So surely you're not staying in the same position. And I guess even if this table turned out to be 24, 24, 24, I'd still be pretty skeptical, Because maybe even if you're in the same position at 41, 43, 45, you don't really know what's happening in between the times, right? Maybe between 41 and 43, the train was moving and just went back to the same position. And between 43 and 45, it was moving and went back to the same position. So unless we're given more information, I don't think you can really figure out whether the train is stopped from looking at the table. You can really only approximate it. But either way, the table clearly shows in this case that we are not being stopped from 41 to 45. So the only correct answer is 18 to 21.